Have you heard of dark matter? This is one topic in astronomy that has fascinated and frustrated scientists because of the mystery surrounding it. Just as the name suggests, there are lots of things we don't know about these mysterious objects, yet they affect the very core of our universe's fabric. However, thanks to the powerful James Webb Space Telescope's latest discovery, our understanding of dark matter is set to increase. What is dark matter? Where did it come from? And how does dark matter affect our planet? Our deep dive into JWST's terrifying dark matter discovery will answer these questions and much more in this video. What is the thing that fills everywhere but that nobody has ever seen? As any astronomer will tell you, the answer is dark matter. In fact, only 5% of the universe is visible, as massive as it is. This includes the Earth, Sun, stars, galaxies, clusters, and so forth. The rest is made up of this mysterious material called dark matter. Dark matter remains invisible because it does not emit light or energy, making it impossible to detect by regular sensors and detectors. What makes up dark matter? Visible matter, also called baryonic matter, consists of baryons. This is an umbrella name for subatomic particles such as protons, neutrons, and electrons. However, scientists believe dark matter is made of non-baryonic matter. The most widely believed candidate is WIMPs, or weakly interacting massive particles. WIMPs are believed to weigh 10 to 100 times the mass of a proton, but they are hard to detect due to their weak interactions with normal. Neutralinos, massive hypothetical particles heavier and slower than neutrinos, are the foremost candidate, even though nobody has succeeded in seeing them yet. You see, space is full of particles that you can't even see or interact with. But of course, another candidate for the composition of dark matter is sterile. Neutrinos are not particles that you see inside regular matter. The Sun constantly releases a stream of neutrinos, but they rarely interact with ordinary matter. In fact, they pass through Earth and its inhabitants, including you, without anybody noticing. There are 3 known types of neutrinos. A fourth, the sterile neutrino, is proposed as a dark matter candidate. The only way sterile neutrinos may interact with regular matter is through gravity. Other possible contents of dark matter include neutral axion and uncharged photinos. Now, there is another material known as antimatter, and that is entirely different from dark matter. Antimatter contains particles that are more or less the same as visible matter particles, but have opposite electrical charges. These particles are antiprotons and positrons and anti-electrons. When you bring an antiparticle to meet a particle, it leads to an explosion that causes the 2 types of matter to cancel each other out. However, since the universe is made of matter, it is obvious there is not that much antimatter around. If not, nothing would be left because everything would have exploded long ago. But interestingly, unlike dark matter, scientists can actually produce antimatter in their laboratories. So how did we end up with the concept of dark matter? Actually, the idea that there might be things in the universe that are invisible to us, emitting no light, is not new. It goes back hundreds of years to the days of Newton. With the discovery of so-called dark nebulae, that is, clouds of interstellar dust blocking the light from background stars, and Pierre Laplace's 18th century speculations about objects which might swallow light, later to become known as black holes, astronomers came to accept the existence of a so-called dark universe. Fast forward to the 20th century, and there was astronomer Fritz Zwicky who, in the 1930s, made the first observations of what we now call dark matter. His 1933 observations of the Coma cluster of galaxies seemed to indicate a mass 500 times more than that previously calculated by the great astronomer Edwin Hubble. Furthermore, this extra mass seemed to be completely invisible. Although Zwicky's observations initially met much skepticism, other astronomers later confirmed them. However, another astronomer, Vera Rubin, would play a huge part in convincing us of the existence of dark matter. 30 years later, Rubin provided a massive piece of evidence for the existence of dark matter. She discovered that the centers of galaxies rotate at the same speed as their extremities instead of rotating faster. Think of it like a vinyl LP on a record deck. Its center spins faster than its edge. so logically the galaxies should behave the same way. However, space is not a place where logic reigns, so galaxies do not behave like a rotating vinyl LP. The only way to explain this is if the whole galaxy is only the center of some much larger structure. Imagine it as only the label on the LP causing the galaxy to have a consistent rotation speed from center to edge. Following the path of Zwicky, Rubin postulated that the missing structure in galaxies is dark matter. Her ideas met much resistance from the astronomical community, but her confirmed observations created pivotal proof of the existence of dark matter. In fact, in honor of this crucial and historic piece of work establishing the existence of dark matter, the revolutionary Large Synoptic Survey Telescope was recently named the Vera C. Rubin Observatory. If we can't see dark matter, why do scientists believe it exists? Turns out seeing is not necessarily believing when it comes to science. The clincher is gravity, that boring stuff you were taught about in high school. Astronomers have hypothesized that the universe must contain more matter than we can see because the gravitational forces that seem to be at play in the universe simply appear stronger than the visible matter alone would account for. Back in the 70s, when astronomers were examining spiral galaxies, they expected to see the material in the center moving faster than the outer edges. However, what they found was that the stars in both the center and outer edges were moving at the same velocity. This proved that the galaxies contained more mass than could be seen. In addition, the studies of gas within elliptical galaxies revealed there should be more mass than what is found in visible objects. So basically, clusters of galaxies would fly apart if only the mass they contained was the mass visible to conventional astronomical measurements. But since that had not happened, there must be something holding them together, and it was agreed to be the unseeable dark matter. While dark matter is present everywhere, it appears different galaxies contain different amounts of dark matter. In 2016, a team led by Van Dockum discovered a galaxy called Dragonfly 44, and the bizarre thing about this galaxy is that it seems to be composed almost entirely of dark matter. On the extreme end, other astronomers have detected several galaxies that seem to have no dark matter at all. Astronomers have been able to create a map of the dark matter in the universe. But how can you map something that you can't even see? Well, the force of gravity doesn't only affect the orbits of stars and galaxies, but also the trajectory of light. Massive objects in the universe bend and distort light because of the force of their gravity. This is called gravitational lensing. It is how light is distorted by galaxy clusters that have helped astronomers to create a map of dark matter. Despite the work of pioneering astronomers, scientists still don't know exactly what dark matter is made of. In fact, they are still working out a way to detect it directly. Currently, scientists are developing such methods with experiments at the Large Hadron Collider (LHC) at CERN, the European Organization for Nuclear Research. This is where the James Webb Space Telescope comes in. Unlike these experiments, the JWST is taking the indirect detection route by studying the effects of dark matter on ordinary visible matter. Now that we know dark matter exists everywhere, where did it come from? There is still debate on that in the scientific community, but there are strong theories. Some scientists theorize that dark matter might be concentrated in black holes, the powerful gates to nothing that, due to the extreme force of their gravity, devour everything in their vicinity. This implies that dark matter would have been created in the Big Bang, together with all other constituting elements of the universe as we see it today. So, in cosmic terms, dark matter particles could be a thermal relic, forged in the hot early universe and then left behind during the transitions to more moderate later eras. One of these transitions, known as freeze-out, changed the nature of the whole universe. What happened during the transition? The universe, as at that time, was so hot that particles were being produced from photons smashing into other photons, photons hitting electrons, and electrons hitting positrons and producing these very heavy particles. The entire cosmos was a particle smashing party. But this party did not last. In fact, it lasted only a trillionth of a second. What followed was the cosmic freeze-out. During the freeze-out, the universe expanded and cooled enough for particles to collide far less frequently and catastrophically. One of these massive particles floating through the universe was finding fewer and fewer antimatter versions of itself to collide with and annihilate. Remember, we mentioned antimatter earlier. Eventually, the universe grew large enough and cold enough that the rate of production and the rate of annihilation basically went to zero. This is the reason many physicists think dark matter is a thermal relic, created in huge numbers before the cosmos was a half-second old and lingering today because it barely interacts with any other particle. In addition, stellar remnants like white dwarfs and neutron stars are believed to contain high amounts of dark matter. This is the same as the so-called brown dwarfs or failed stars that didn't accumulate enough material to kickstart nuclear fusion in their cores. Scientists have three classifications of dark matter developed in the 80s. They are cold, warm, and hot. However, these labels have nothing to do with temperature. They are based on how fast each type of dark matter would have traveled through the early universe, a speed that depended on its mass and how hot its surroundings were when it popped into existence. Light, fast particles are hot dark matter, heavy, slow ones are cold dark matter, and warm dark matter falls somewhere in between. Using this classification, WIMPs are cold, sterile neutrinos are warm, and relic neutrinos from the early universe are hot. Axions are, well, a special case. They are both light and extremely cold. What is the implication of the speeds of dark matter particles? According to a scientist, if a dark matter particle is lighter and faster, it can travel farther in a given time, and it will smooth out any structure that already exists along the way. On the other hand, slower, colder forms of dark matter would have helped build structure. Most of the dark matter particles would have been created by collisions between other particles in the hot, dense soup of the infinite universe. There is a similar process today, that is, the way that high-energy particle collisions at places like the Large Hadron Collider give rise to exotic new types of particles. As the universe expanded and cooled, dark matter particles would have wound up being hot, warm, or cold, and in fact, there could have been more than one type. Each type of dark matter would have had a different impact on the growth of structure along the way. Either it was adding to the universe's clumpiness, and thus to the building of galaxies, or doing the opposite by thwarting their growth. Cold dark matter would have been a clump builder. It moved slowly enough to cluster together and create gravitational wells that would have captured nearby bits of matter. However, hot dark matter would have been a clump smoother. It would have sped by so fast that it could overcome the attractive force of those gravitational wells. This, of course, means if all dark matter were hot, none of those seeds could have grown into the bigger structures that we have today, and this is why scientists believe that hot dark matter particles, such as relic neutrinos from the early days of the cosmos, could not have been more than a sliver of dark matter as a whole. Remember we said axions are a special case. They would be both extremely light and extremely cold. They are so weakly coupled to other forms of matter that the frantic collisions of particles in the thermal bath of the early universe would have produced hardly any, so they would have been produced differently from the other dark matter candidates. Despite the universe being very hot at the time, axions would have been very cold at birth and would stay cold forever, which means that they are absolutely cold dark matter. Axions are very light, but since they exist close to the temperature where all motion stops, they're essentially not moving. You can call them ghostly fluid, and everything else moves through them. Dark matter is invisible, so how do scientists study it? There are two approaches, basically based on the discipline of the researchers. For astronomers, it involves looking at the clustering of material and the motion of objects in the universe. Particle physicists, on the other hand, attempt to detect the fundamental particles that constitute dark matter. The International Space Station has an experiment called the Alpha Magnetic Spectrometer (AMS), which detects antimatter in cosmic rays. Since 2011, it has recorded more than 100 billion hits by cosmic rays, and this has provided intriguing insights into the composition of particles moving through the universe. Samuel Ting is the AMS lead scientist and a Nobel laureate with the Massachusetts Institute of Technology. He said they had measured an excess of positrons, that is, the antimatter counterpart to an electron, and this excess can come from dark matter. But he added that they still need more data to ensure it is from dark matter and not from some unknown astrophysics sources. Perhaps in a few more years they can make that determination. Apart from the AMS, some telescopes in Earth's orbit are hunting for the effects of dark matter. This included the European Space Agency's Planck spacecraft, which was retired in 2013. It spent 4 years in the Lagrangian point 2, where the JWST is located, mapping the distribution of the cosmic microwave background, a relic from the Big Bang in the universe. Irregularities in the distribution of this microwave background revealed clues about the distribution of dark matter. However, space is not the only place where dark matter is being studied. On Earth, under a mountain in Italy, the LNG's Xenon 1T is searching for telltale signs of interactions after WIMPs collide with xenon atoms. This first-of-its-kind project gives scientists an opportunity to detect dark matter with ultra-low background massive detectors on Earth. Another dark matter project is the Large Underground Xenon Experiment LUX, located in a gold mine in South Dakota, the US. It has also been hunting for signs of WIMP and xenon interactions. The Ice Cube Neutrino Observatory, an experiment buried under the frozen surface of Antarctica, is hunting for the hypothetical sterile neutrinos. NASA scientists have used the Fermi Gamma Ray Space Telescope to make maps of the heart of our galaxy, the Milky Way, in gamma-ray light, revealing an excess of gamma-ray emissions extending from its core. The signal found couldn't be explained by currently proposed alternatives, but it strongly suggests the existence of simple dark matter. What makes the JWST capable? Well, when you observe dark matter, you have to sort of always go in a roundabout way because you can't see it. But Webb does have the capability to try and get at that in new orthogonal ways, looking at the dynamics of galaxies. For example, as a roundabout method of detecting dark matter, astronomers can use existing technologies to measure how much mass is in stars and galaxies. Some of the primary evidence for the existence of dark matter is that many galaxies could not exist and move as they do without a large amount of invisible mass. To help astronomers locate that dark matter more precisely, the JWST will take extremely sharp images in which researchers will be able to observe disturbances caused by gravitational lensing, pointing them to where the invisible mass is lurking. By the way, gravitational lensing is a phenomenon described by Einstein's general theory of relativity. With this phenomenon, when a light beam passes a large mass, it will be slightly deflected as the fabric of space-time is slightly curved by the mass. By imaging distant galaxies, the JWST can detect these masses and determine what is missing or not observable. This is likely to be dark matter. The new space telescope is particularly well suited. One of the researchers that can't wait to use the JWST is Professor Matthew Walker of the Carnegie Mellon University. He is the principal investigator of a program that will make use of data collected in the telescope's first year of operation. He is going to work on dark matter, but with a twist. Cold dark matter theory, which predicts that dark matter exists in clumps called halos with small basic units, as opposed to galaxy-sized agglomerations. Walker and his team will look for perturbations from subgalactic dark matter halos on very fragile gravitational systems. Now, there is something to note about the JWST which we will quickly go over here. The telescope is optimized as an infrared telescope for peering deep into the past and outer reaches of the cosmos, a narrow field of view instrument for looking at single objects very closely. That is exactly the qualities you want for imaging the first stars in the universe and studying the atmosphere of distant worlds, but you can do better when studying dark matter and dark energy. Telescopes that are optimized to study dark energy try to observe a large fraction of the sky. The way we learn about it and measure it is by adding up its consequences over a lot of space or a lot of volume. However, the upcoming Nancy Grace Roman telescope, expected to launch in 2027, will, by contrast, sport a wide field of view capable of imaging wide swathes of sky, which is exactly what you need to measure the effects of mysterious forces on large structures or portions of the universe. The JWST and Nancy Grace Roman could, however, work together once Roman is deployed. This is because while Roman may identify hundreds of distant supernovae, it will be JWST's job to make the most precise measurements of those distant lampposts possible. Stay tuned to this channel as we will bring you all the details about the Nancy Grace Roman telescope. Let's hear what you think.